Okay, so yeah, my name is Surya Ganguli. I'm going to talk to you about learning deep generative models by reversing diffusion, essentially reversing the flow of time. So this is work led by my postdoc, Josh Soldikshin, who's now at Google Brain Research, and it's kind of reporting on a paper whose title is Deep Unsupervised Learning Using Non-Equilibrium Thermodynamics, and you'll see why we kind of use that name. So, you know, when we learn generative models, the first thing we're kind of faced with is a flexibility-tractability trade-off, right? What we'd like to do is we'd like to easily fit a very flexible probability distribution so that we can model high-dimensional, complicated data distributions. But the more flexible they get, the harder they are to fit, right? So we can all easily fit Gaussian distributions just by computing first and second order statistics of our data, but they're not very flexible. And as we go up the chain, we can get very complex non-parametric or energy-based variational approaches to fit models, but again, they're difficult to fit, right? Although they are quite flexible. So we'd like to be somewhere around here. That's kind of the sweet spot. That's what we'd like to get to. And so I'll offer you kind of one possible way of getting here, though we don't fully understand theoretically the degree to which, we don't have quantitative measures on these axes, so we can't definitively say that, that it's up here. But it's sort of qualitatively, it's both easy to fit and quite flexible. So what's the idea? The essential idea was inspired by physics, actually. So the physical motivation is, well, data distributions are often complex and high-dimensional. We don't, over high-dimensional spaces, we don't have mathematical control over them. So let's just destroy the data, right, and make it simpler. So let's destroy structure and data through a diffusive process. But let's carefully record that destruction of structure, like sort of in terms of a movie. And then we'll use a deep neural network to reverse the flow of time and then essentially create structure from noise. So the destructive process destroys the structure and data to turn data into noise. And then deep neural networks reverse that flow of time. And it's actually inspired by recent results in non-equilibrium physical mechanics, which show that entropy can transiently decrease for short time scales, sort of giving you transient quote-unquote violations of the second law of thermodynamics, and I'll talk more about that in a bit. So again, just the picture is, let's say this is a complicated data distribution, as represented schematically by this die. Let's let the data diffuse. So if you undergo physical diffusion, over time the stationary state will be the uniform distribution. It'll definitely be simpler. We know how to sample for the uniform distribution. Then we can create a generative model of the complex data distribution by sampling from the uniform distribution and feeding it into any system that can reverse the flow of time in this movie. So we're gonna use deep neural networks for that. We can recover a data distribution by starting from uniform distribution and running the dynamics backwards. So again, this was inspired by the so-called Jasinski equality. So basically, the second law of thermodynamics tells you that if any process is left to its own devices, in general, the entropy of the process will increase. So, a small ball of gas will become a larger ball of gas if there's room. So entropy will increase. But that actually only happens on average. For small periods of time, it's a statistical law. So for small periods of time or for small systems, entropy can transiently decrease. So I don't know if you've heard about this, but there's something called the Jasinski equality, which is the most exciting development in non-equilibrium physics, in the last 10 years. This actually says that there's an equality, right? That for any stochastic process, that has detailed balance, e to the minus change in entropy from the beginning of the process to the end of the process, on average, is equal to 1. Okay? Now, if you apply Jensen's inequality to this using the convexity of e to the minus x, this actually follows. So remarkably, this age-old theorem, or idea, or law, the second law of thermodynamics, follows as a corollary of a much more profound equality, just through application of Jensen's inequality. So the way that you prove this is you carefully think about the probability distribution for forward paths through the physics, and the probability for the reverse path occurring, and you look at log probability ratios of forward over reverse trajectories. Okay? And so inspired by the ideas in that proof, we said, well, how can we help ourselves? So this is essentially telling you that sometimes delta S can be negative, which means you can create structure from noise. But how can we help ourselves along? Well, what we can do is we can change the physics of the reverse process and replace it with a neural network. Okay, so let me now just demonstrate how it works. So the simplest example is a Swiss roll, right? Okay, great. So here what we'll do, so this is a toy example. We'll go to progressively more complex examples. So this is a toy model of a complicated data distribution living in 2 dimensions. These are the data points. So in the process of destroying structure, we'll let each point diffuse in a 2-dimensional plane, but with a restoring force to the origin. So the data points are like thermal particles that diffuse around, but they're connected to the origin with a spring. So it's literally an Ornstein-Uhlenbeck process. The stationary distribution is an isotropic Gaussian for that process. And this is an example of the record of destruction of structure. So this is a movie, and you just saw the structure getting destroyed. So we're going to feed these movies to train a deep neural network that takes as input any point in the space and spits out a vector and a covariance matrix for a little reverse diffusive step. Right? And so we can learn essentially a way to reverse this dynamics, and each layer of the neural network is responsible for reversing one frame in the movie. So there's a one-to-one correspondence between frames in the destructive process and layers in the reverse neural network process. So if we train the network on that data, then what happens, if it works, we should be able to sample from a Gaussian distribution and feed it through the trained stochastic dynamical system to get a deep generative model of the Swiss roll. And so this is what happens, essentially. So the Gaussian noise under the neural network dynamics turns into a Swiss roll. And it's a bit approximate. There's some stragglers out here, but it sort of largely gets the structure. So what is it that the system is learning? Right, it's actually learning a vector field. Okay, so what it's doing is it's learning a time-dependent vector field. So this is the vector field that's learned early. So this is going from here back to here. So this is the forward diffusive process. This is the reverse neural network process. Early on, it learns a vector field that's quite small. And then later on, it learns a vector field that gets larger in magnitude. And as you can see, the vector field pushes you to the Swiss roll. How do you understand the nature of this vector field? Well, if you think about the training data, let's think about the training data that got to here, right, at a certain time. In the diffusive process that got to this point, what we have to think about is the conditional distribution of the past in the destructive process, given that the destructive process got you to here. So if this point is over here, then that conditional distribution is closer to the Swiss roll and over here. So the neural network learns a strong vector field going this way. However, if it's in the middle, the conditional distribution of the past, given you're somewhere in the middle of the Swiss roll, you could have come from either end. So the center of mass of that distribution is where you are, so the vector field that's learned is 0. So essentially the system is learning the conditional distribution of the past, given the present in the destructive process. Okay. So let's move on to some more complicated examples. Actually, I should show you. Right, so the next thing we looked at was a toy model of natural images. So these are, for example, the dead leaves model. So the dead leaves model is a toy model of natural images that throws down circles of different radii with a power law distribution of radii to mimic the scale-free nature of natural scenes. Each time a circle is thrown down, it occludes all previous circles. So it captures a lot of the low-level structure of natural scenes, including its power law behavior, occlusion, edges, angular correlations along edges, and so on. And so we trained a convolutional neural network to reverse the flow of time in a diffusion process, where each pixel essentially diffused independently of every other pixel. So that turns dead leaves images into white noise. And then if the neural network works, we should be able to turn white noise into a sample from the dead leaves. So let me just show you that. So this is the neural network. I'm feeding into it a very large white noise image. And over time, it will turn into its best guess as to what a dead leaf is. Right? So it's not perfect, you don't see the circles, but you do get the coarse features. You get regions of large homogeneity, sharp edges, angular correlations in the angle of the edge over long ranges, and so on. And you actually sort of get a power law distribution of the sizes of homogeneous regions. So you got a lot of structure there. And we also computed the log likelihood of the dead leaves under our model. And at the time of publication, it was about a year and a half ago, it was state of the art. Although I'm not sure if anyone has actually specifically tried dead leaves on other generative models. We can also sample from conditional distributions as well by clamping some of the pixels and letting the others evolve. So we also trained our model on, say, textures of bark, right? And so here's an example of a texture of bark where the exterior has been clamped and the interior has been replaced with white noise. So this is like an inpainting or denoising problem. And so what will happen is the convolutional neural network, some of the convolutional filters will overlap here, and so information from the boundary will propagate into the interior and fill in your best guess for the bark. Right? So this is the model at work. So it's turning the white noise into the best guess for what it would think is in the interior. So just qualitatively it looks sort of realistic, but it doesn't actually recover the exact image. It actually recovers a different image because it's sampling. So let me show you that. That's the dead leaves. Oh, it actually works on here. Interesting. Yeah, so this is a sample from the sort of the next best model, and this is the sample from our model. And we can evaluate the log likelihood. Oh, by the way, that's also interesting. We can evaluate lower bounds on the log likelihood of a data point also. So evaluating that is cheap in this model, and I'll explain how we do that. Okay, so these are examples of the bark that we trained on, a bark data set that we trained on. And okay, so yeah, again, it works here. So this was the original bark, this is the recovered bark, and as you can see, the interior is different, right, than this one. Mm-hmm. So again, that's an artifact of the fact that it's sampling, not deterministically auto-encoding. Okay, so these are examples on CFAR10. So these are, so we trained this reversal of diffusion on CFAR10. This is a bunch of held out images that the neural network had never seen before in the training. These are noisy versions of the images where additive pixel noise was, the pixels were scrambled with an SNR of 1, right? And this is the denoised versions of these. So there's a one-to-one correspondence between images here and images here. So for example, this car and this car is here. And these are samples from these images. Okay. So of course, there's been a lot of work on generative models, in particular GANs and VAEs and so forth. GANs get you extremely good samples, but you can't compute log probabilities with them. Variational autoencoders are related to this in the following sense. In a variational autoencoder, you have a recognition model that transforms data into a simple representation, and then a decoder generative model that transforms that simple representation back into the data distribution, and you jointly train them, right? And those are actually a little bit difficult to fit, so you can't fit variational autoencoders with many, many layers, right? Here we can fit about 1,000 layers, for example. And the reason is that we're to frame this work in that language, our recognition model is fixed and it's diffusion and it's not learned. And the generative model is learned, right? So that actually makes it quite easy to fit this model, and I'll say more about that later. But of course, we cannot have the expressive capacity of variational autoencoders because that involves joint training of the recognition and generative model. But we achieve more tractability in terms of learning. So we're sitting at a different point on the flexibility-tractability trade-off compared to that. So basically, the summary is training is extremely tractable. Each layer of the neural network simply has to estimate a mean or a delta shift and a covariance matrix to reverse the flow of time one step in a movie. That's all it needs to do. And that's pretty easy to do. The magic is that the concatenation of that many steps yields a reasonable composite map. And that's where the magic lies. Sampling can be made exact. This can be made exact in the limit in which so we have a proof that if the diffusive destruction of structure is very, very slow, and the reverse neural network has many, many corresponding layers, then you're sort of in the slow adiabatic limit is what we call it in non-group thermodynamics. And the model distribution will converge to the data distribution. Of course, given enough data, then this will happen. So if you're not running the sample complexity problems, then you can prove that there's a limit in which you can exactly sample from your data distribution. Inference is also easy via sampling, and also it's actually quite cheap to compute the log probability of a data point, essentially using ideas from importance sampling. So what you do is let's say you want to evaluate the probability of a data point. You don't know what the high-level representation, the generative model is for that data point, but what you can do is you can run that data point through the diffusive process to get a trajectory and compute the log probability ratio of that trajectory under the diffusion in the numerator and the generative model in the denominator. And that we can prove is a lower bound on the log probability of that data. So you can at least compute lower bounds on the log probability. Okay, there's sort of two, I think, key ideas that may be generalizable to other kind of research. There's sort of two vexing problems in both neural networks and sampling, and those are the following. The first is the spatial credit assignment problem. So if you have a neural network with thousands of layers, and the output makes a mistake, you have to figure out how to change the synapses far from the output. And we solve that using backpropagation, and that has its own issues with vanishing and exploding gradients. So we circumvent the spatial credit assignment problem here by essentially providing targets to every single layer, right? So each layer knows what its input is. It's the destructive process at time t, and it knows what its output should be. It's the destructive process at time t minus 1. Right, so it knows its input and output, so you don't have to solve any spatial credit assignment problem across layers, even though you're training thousands of layers simultaneously. Okay, so that's kind of idea number one. Now, idea number two, or problem number two, that we often run into, is if we want to sample from a very, very complex distribution with multiple modes, then you run into a mixing time problem, because it takes a long time to hop from one mode of a distribution to another. In fact, if you write it as an energy wells, the barrier hopping time is e to the minus height of the energy wells. So it's exponentially long, or 1 over that. So it's exponentially long times to hop between wells. That's the mixing problem. And if you need to learn probabilistic models where inference is part of your internal loop, that makes learning very intractable. So it's incredibly important to solve this mixing problem. We circumvent this mixing problem. So how do people, so oftentimes what you do is you model the data distribution as the stationary distribution of a stochastic process, where that stochastic process obeys detailed balance with respect to the desired distribution. So then that's when you run into the mixing problem. So we circumvent the mixing problem by not modeling the data distribution as the stationary distribution of any stochastic process. What we do is we model the data distribution as the outcome of a transient process. Right, you start from at time t and you go back to time 0. You reverse the flow of time in a diffusion process that only evolved for a finite amount of time. That's why it's kind of a non-equilibrium process. And then we build into the training the demand that you get from a simple distribution to the data distribution in a finite number of steps. So we're demanding that the neural network find a good model of the data distribution in a finite amount of time. And therefore we don't run into the mixing problem as much as you would otherwise do if you just demanded that a Markov chain mix to get to the data distribution, to map its stationary distribution to the data distribution. So I think those are kind of two key ideas in this work. And there may be ways to port these two key ideas to other scenarios. So basically provide targets at every layer for your neural network and don't model data distributions as stationary distributions. Okay, so again, so it's a short talk. I'd like to, again, thank my funding. And again, Joshua was kind of the ringleader of this project, and it was also work with two very talented graduate students, Eric Weiss and Niru Maheswaran. All right, thanks.
Questions? We have time for one question.
Oh, go ahead.
So if I understand, you look at one movie and learn the dynamics in reverse. What if you want to train, you have several different movies and you want to have the same network express each sort of generation process?
Yeah, so the framework is always that there's one data distribution, right? And you can generate multiple movies by sampling different data points and then having each data point, which is usually a vector in a high-dimensional space, diffuse in that high-dimensional space. So each data point gives you one movie or record of destruction of structure. And then you get many, many, many of those movies and you train in a batch gradient descent on that. That's how we do it. The Swiss roll was a bit misleading because there were multiple data points in one movie. But what's actually happening is for the images, say you start with a dead leaves image, and you have it diffused to white noise. That's one movie for one data point. Another image, right, and so on. The Swiss roll is misleading because we can put all the data points in one figure.
Yeah, actually, one question, I don't know if this intuition makes sense, but if you would make this destructive process less diffusive and somehow more ballistic, such that it equilibrates faster.
Yeah, that's actually bad.
So
yeah, that's bad.
My intuition would be that you would need actually fewer layers because it would kind of...
Yeah, you could, but then you lose the training signal for the neural network. So remember, the training signal is the conditional distribution of the past given the present location. That's what trains the neural network at that present location. So you want that distribution to have information about where you came from. So if the diffusive process is too ballistic, you lose that information. So there's kind of this trade-off between, of course, how fast you make the diffusion and how many layers you need in the neural network. But then you lose, so you could make the thing shallower, but you lose the learning signal. So you have to play a little bit with that diffusion schedule. We actually learned that diffusion schedule.
We can take one more question as Guillaume sets up.
Last question. Over here.
Oh, yeah.
So I think what is interesting was it tells you that there is a way of learning generative models which don't necessarily involve the problem of posterior inference. So GANs also offer a very similar solution. They tell you there's a way of training generative models without computing the posterior. But I'm curious to know, what do you think is the principle that if I wanted to derive the learning rule that you're doing, so for variational inference, I know I can compute the free energy by computing the low bound and the marginal, and that gives me a way of doing
Actually, we do it exactly that way. So we maximize the log probability of the data by minimizing essentially the KL divergence between the destructive process and the time reverse of the generative process. So we actually, and we optimize the variational lower bound on that. Yeah, so those details are on the paper.
Take a speaker.